Let's go over question number 2 in activity 11. And in this, we're going to develop a model to try to predict whether or not a customer was reacquired after being offered some special discount or some special offer to try to entice them back. So this data is the cust reacquire data frame. And part A has us to search for a model while considering all two-way interactions between a specific set of variables. So with this data set, we're interested in predicting a categorical response, either yes or no, for whether or not the customer reacquired, and we're going to use logistic regression for that, and logistic regression is just very slow. So actually doing an all possible procedure isn't really what we want to be doing here because we don't have, a whole day for our code to run. So let's start out with the search procedure with the naive model, see what we get, and then see with the full model, if we start there, what we end up getting. They might converge to different models here. So let's start out by fitting the naive model, and since it is logistic regression, we'll use GLM here, and we want to predict reacquire from twiddle 1. With the naive model, we're not predicting it based on anything, it's basically just majority rules, and we encode that with a twiddle 1. And we need that in the cust reacquire data frame. And because we're doing logistic regression, we need to make sure to turn on the logistic feature of the GLM command by doing family equals binomial. So we fit the naive model. And now the full model, the most complex model that we want to consider during our search, well, we want to consider all predictors and all two-way interactions between this specific set of variables. So I'm going to make my life just a little bit easier and paste this down here. We want to be doing reacquire twiddle, and then since I have a specific set of variables that I want to consider the interactions between, not all variables in the data frame, I'm just going to separate all those predictors by a plus sign, kind of make sure that's wrapped inside parentheses, and then outside the parentheses I'll put a caret 2 so that it considers the interactions between just that specific set. So I also need to put in the data argument and the family equals binomial, so we should be good to go with this. So we can run this. And now for our first search procedure, we're going to start out with the naive model. So the first argument of step, which is our search procedure, is what model we want to start out with. And so we'll start out with absolutely nothing in our model and then tweak that piece by piece, either add in a new predictor or kick out something that's already in the model. So the scope argument is always going to be the same, directions equals both. Trace equals to 0 is going to suppress any sort of output, and in this case I'm interested in actually looking how the search is being completed. So I'm going to click run here, and it'll give me a narrative for what happened with this model as things were being modified. So it looks like at the end of the day, my model is predicting reacquire from the customer lifetime 1 plus lapse, offer, age, and then also the interaction between offer and age here. All right, well, let's also consider a different search. Let's consider starting out with the full model here, the most complex model, and seeing what that leads us to. Sometimes we end up with different models, so it's always good to start with both the full and the naive to see if we do end up with something different. And in this case, we do. We see that there's an additional predictor here, the interaction between gender and age, and then also gender as a predictor by itself. All right, so what predictors are found in the model that we get if we start out the search with the naive model? Well, since I saved that to S1, I can look at the predictors, and I see that lifetime 1 is there, lapse is there, offer amount, age, and then the interaction between the offer amount and age. All right, that is offer amount, age interaction here. What additional predictors are in the model found starting with the full model? I'll just remind myself what's there. Lifetime 1 is there, lapse is there, offer amount, age is there, the interaction between offer and age, and we also see gender and age, that interaction there. So gender and the gender age interaction. Oh, kind of interesting. So we might be interested in knowing, well, which one's kind of the better model here. Our boss wants us to choose between these two models. Which ones do we pick? Well, that's where we look at the AICs. So the AIC of S2, started with the full model, is 2 246.12. AIC of S1, which is the one that we started with, the naive model, is, and that's already forgot it, so let's actually just run that procedure once again, and it tells us the AIC at the very bottom here at the last step. This AIC is 245.2. So the difference in AICs between these two models is less than 2, so there's no compelling reason to really choose one versus the other from a statistical point of view. And so in this case, it makes sense to just go, with the simpler model. It has fewer interactions, it's easy to interpret, so we could go ahead and choose the simpler one here. So I would pick the one found starting with the naive model, since it is simpler and it has an AIC within 2 of the other. No compelling statistical reason to choose the lower AIC model here, since it is more complex. And a difference in 2 is never compelling reason to choose one versus the other here. All right, using the selected model, describe how the probability of reacquisition varies with the variable lapse. So let's look at a summary of that model here. And we see that lapse is not involved in an interaction, so we can immediately interpret the coefficient here. We see that the coefficient is negative, implying that if we were to compare two individuals who differed in lapse, we would expect that the person with the larger value of lapse to have the smaller probability of our level of interest. Now in this case, the thing we're predicting is reacquisition. The levels are no and yes, and so our model is predicting the probability of yes. So people with larger values of lapse have a smaller probability of being reacquired, and that confirms what we might expect with intuition. So individuals with larger values of lapse, in other words, those that have been away from the company for longer, have a smaller probability of being required. Smaller probability of being reacquired. Coefficient was negative. That's how we know. All right, a search for a descriptive model will have failed if the selected model does not provide a reasonable reflection of reality. So although we've selected between two models, and it looks like they're both about equally as close to the truth, the AIC actually doesn't tell us whether or not it's a reasonable reflection of reality. We still need to check that regression. And so let's check regression on that model to see if we pass the statistical test. With logistic regression, we can't really look at plots for this, so we rely on two opinions on whether or not the assumptions are met. And in this case, the p-values of both tests are bigger than 5%, so we pass the test for the assumptions here. So it looks like this is a reasonable descriptive model since we pass the tests for the assumptions. Both p-values are bigger than 5%. So great, it looks like our model does provide a reasonable description of the relationships, so we can use it to describe who has the bigger probability of being reacquired. All right, well now let's imagine building a predictive model. Now we don't really necessarily care how close to the truth our selected model is, we're just interested in it making predictions on genuinely new data here. So to do that, we need to take our original data, split it into two. We need a holdout sample so that when we're done selecting our model, we can check to see if it really is generalizing well to new data. The data in the holdout sample, none of the models will have seen before, so we can check to see if the error that the model's making on the holdout is about what we expected. So to do this, well, the selection into random or into training and holdout sample is done at random here. So we prime the random number seed. And in this case, we're going to take 60% of the original data to serve as our training sample and the remaining 40% to be in the holdout sample. So we'll define the train rows, holdout, and train. And then we're going to use build model to try to come up with a decent predictive model here. So in this case, what we're going to do is make our task a little bit simpler. It's preferable, of course, to run this procedure considering all two-way interactions, but this literally will take hours to run. Logistic regression is very, very slow. So in this case, what we're going to do is just consider the variables: lifetime 1, offer amount, lapse, price change, gender, and age. No interactions. Simplify our problem. There very well could be a better predictive model out there that we're not going to find by doing this, but this will allow us to actually complete this in a reasonable amount of time. So we'll run build model here, making sure the seed is at 320. The generalization error of these models are estimated with a random procedure that repeated k-fold cross-validation. So we need to make sure that if we want to reproduce the results, the seed argument is there. All right, so what are some results? What we see is that the misclassification rate, the estimated generalization error of these models, looks to decrease as we make our model more complex, as we add in more predictors, up to a point. There's a small hint that the model starts to become overfit, basically memorizing the set of quirks and characteristics that are particular to this set of training data, making it unable to generalize to new data as a whole, when we make the model a little bit too complex here. But it looks like if we wanted to go with the model with the absolute lowest estimated generalization error, we would have these 4 variables in it. If we wanted to get away with a simpler model whose error looked to be comparable to the overall lowest, well, we can use the 1 standard deviation rule. Any model whose estimated generalization error is within 1 standard deviation of the overall lowest is okay. And so in this case, we could get away with a slightly simpler model with just 3 variables here. So, all right, if we did this, then maybe this is few enough variables that we can actually consider the interactions between them. So let's actually copy these 3 variables, put them inside parentheses, square that so that we consider those 3 variables and the two-way interactions just between that set. So let's do this and see what we can end up getting. We see that the model selected with the 1 standard deviation rule actually does include the interaction between lifetime and offer amount. But there's really very little difference between the model selected with the 1 standard deviation rule and the one with the overall lowest estimated generalization error. So based on the work that we have done, we would either select the model with the lowest estimated generalization error, this guy right here, or the model selected with the 1 standard deviation rule. And there's no compelling reason to choose one versus the other based on the analysis. The estimated generalization errors are close enough here. So let's just actually see how each of these models end up doing. We've reserved that holdout sample. None of these models have seen it yet. So the generalization error on the holdout sample is kind of an honest estimate of how well we would expect these models to be doing on brand new data, because the holdout sample, for all intents and purposes, is brand new in this case. So all right, let's try this out. Let's fit the naive model, basically the majority rules data model here, basically no model whatsoever. Reacquire twiddle 1, making sure to build that on the training data, and let's see how well that generalizes to the holdout sample. Well, in this case, the misclassification rate is 37%. Not that great, so that's the baseline. Let's see if we can beat that. Well, without any sort of model building procedure, just straight up predicting the probability of reacquiring based on all the predictor variables that we have available to us, based on the training set, we can see how well we do. And in this case, I made it a little bit too easy. I included some additional variables that I wasn't really allowed to actually use, namely lifetime 2 and value 2, basically what happens after that customer was reacquired. These are all 0 for customers that were not reacquired. And so if I use information about what happens after the customers have been reacquired, obviously I can perfectly predict who did and who didn't. Basically, if the 0s in lifetime 2, they weren't reacquired. So that's not really what I want to be doing. So instead, I can take out those 2 variables, lifetime 2 and value 2, twiddle dot minus those 2 variables, and see really how I'm doing. Oops, value 2. All right, so in that case, my misclassification rate is 13.5%. So much better than the naive model. So if I just straight up fit the model with all the predictors I had available to me that were, fair predictors, then that would be my misclassification rate. I'm going to delete this model here, the model with the two-way interactions. Actually, no, I won't, because I've already started this out. Basically, if I didn't do any model building procedure, these are the predictors I can use. And so I can, instead of doing twiddle.squared, which uses those illegal predictors, let's just stick with those predictors squared. All two-way interactions. Probably an overfit model, but let's see. Ends up giving out the same misclassification rate. What about the models that we found via our search procedures? Well, we can fit both of those, extracting the formula with just the formula command. So do that. 12.5%, a little bit better. Searching for a model that gets closer to the truth, at least. Not necessarily intended to make great predictions on new data, but in this case we see that it does pretty well. What about the other search that started with the full model? Slightly worse. All right, so now what about the models that we actually found as we were trying to build one for predictive purposes? So this is one that had the overall lowest estimated generalization error found over our procedure. Let's see how well that ends up doing. 13%, actually better than all the ones so far, so thumbs up for our model building procedure. What about the one selected by the one standard deviation rule? Here we're not considering any interactions. 16.5%, not quite as good here. All right, so we ran the following code. We found the estimated generalization error on the holdout sample. What model ends up predicting the best on the holdout sample? Well, it turns out it's the one that had the overall lowest estimated generalization error when we ignore the two-way interactions. Now, I haven't given you the code that actually fits the model that has the interactions in there. I ran them on my own time, and I didn't find them to do any better here. So it looks like the model with the lowest estimated generalization error has the lowest misclassification rate on the holdout sample. Victory for our procedure. And this doesn't always happen. Very often it'll turn out to be the case that the model that we selected during our model building procedure actually is beat out by some other model, but there's no way we would have known that ahead of time. So predictive modeling is all about trying out a whole bunch of models, estimating how well we think those models are going to do, and just select the best that we can. Cross our fingers that it will end up doing reasonably well on new data, but of course very often there actually will be other models out there that will end up predicting better in reality. But there's no way to know that ahead of time.